All right. Hello, everyone. Good afternoon, and welcome to today's installment in the Electric Avenue webinar series presented by eMERGE Alliance, a trusted RE+ events partner. Thank you for joining us. This afternoon's webinar is a grid's best friend, microgrids for utility scale. There will be a recording available afterwards for viewing on the RE+ website, that is re-plus.com. And we will also send a viewing link out via email to everyone who registered. And now it's my pleasure to introduce the co-founder and president of eMERGE Alliance, Brian Patterson.
Thank you very much, Trish, and welcome everybody. As advertised, we're going to talk about microgrids, a kind of a unique view of microgrids that utilities might be very interested in, but can also be participated in by third parties and others. So our special guest today, and we're really honored to have Rob Bennett, who is the president and chief executive officer of Emera Technologies, and they're makers of something called Block Energy, and we'll talk about that later in the program. But to get started today, what I wanted to do is kind of set up the problem that we're trying to solve, and that is, what challenges the grid faces going forward, and how potentially microgrids are becoming part of the solution set to meet those challenges. So let's tick off a few challenges that we think the grid is up against these days. One is just simply the sheer amount of electricity needed, and it's really outstripping, in many cases, the available supply. And the killer apps here are really things like electrifying transportation and the implementation of highly efficient, but albeit new to the electric field, electric heat pumps for heating and air conditioning. And then there's just a general increase in the use of electronic information and communication and things like industrial robots. And all these things are relatively new for loads for electricity. And you can kind of look at them as sort of the killer apps of what the grid is facing going forward. And then if you add to that simple population growth, there's really a tremendous need to increase production. So what are we doing about it? Well, the answer today is we're trying to increase the generation of electricity. It's kind of simple, or is it? Because traditional generation techniques have traditionally relied on some form of fossil fuel, and this approach is kind of fraught, as you know, with economic and environmental and political challenges. And even those challenges aren't enough, because central production, particularly things like wind and solar, still leaves transmission and distribution systems with the burden of delivering the new bulk power to distant users. And that's trying to do that without physical disruption and transmission loss through the system. So another set of challenges is what utilities often talk about as system destabilization as a result of trying to patch in, if you will, intermittent energy sources. And these energy sources are growing. I read one report recently that said that it could be greater than 50%. I think the number in the report was 62% of generated electricity is going to be covered by distributed and intermittent sources, such as renewables in most cases. However, connecting these sources to the grid is not as simple as it may seem. And there's a variety of highly variable conditions and such like weather that affect their intermittency, and just day-night when it comes to solar. So as such, DERs generally are considered unstable energy sources, and left unmanaged, they can cause serious grid imbalances. So the solution there, thankfully, at least at the bulk level, is to add electricity accumulation, if you will, or batteries or others, energy storage systems that can store initially unused electricity and save it for later to provide a smoothing effect and correction of things like frequency corruption or voltage drops and things. Now, artificial intelligence has been improving this kind of predictive capability of these systems, but most distributed storage is natively DC. So this can require additional electronics and double conversions, and then of course there's the requirement of supply synchronization when the power is returned to the grid, because the grid is an AC grid. The next challenge the grid has is the increasing number of power outages for a variety of reasons that it faces. Two most common causes, of course, for blackouts are extreme weather conditions, and more and more recently, we've heard about time-worn kind of power line damage and things like that. Serious cases of power outages have in fact threatened millions of people, in billion-dollar type damages across the country. And within these paralyzed areas, these potentially huge blackouts can cause other damages that aren't, or other damage that isn't so obvious, like electronic device damage or food and water spoilage. Supply storage spoilage, or important data losses off of communication and information systems. And as electric transportation and heating and cooling with electrical devices increase, the effect of power losses during these catastrophes will be all that more damaging. So now there are some solutions being applied, faster detection and response to power line issues and so on. But frankly, at relatively high cost, and surely with the necessary existing lines, we can afford to find a different system architecture for new lines or new distribution. And really, that's a little bit about what we're going to talk about with microgrids. But as more electricity generally means more lines, at least if we follow today's 100-year-old paradigm, and the cost of physically protecting those lines and providing fast rerouting mitigation and so on is really daunting. The next set of problems is really with all good intention. Electric mobility demand is going to cause some interesting challenges. First, EVs right now are relatively rare, but they're fast arriving on the scene, as you can see in this pictures here. But EV charging can be slow, and if you try to speed it up, it can really peak the demand for immense amounts of electricity. One full fast charge of just a passenger car equals a startup and running of about 70 air conditioners simultaneously. That's a big demand on the grid just from one vehicle at a time. So the instant changes in power demand are a huge problem for the grid, and peak demands will make the kind of proverbial duck curve look like a kid's bath toy, frankly, in comparison, at least. But the solution is, let's make the grid smarter. Let's manage these online connections to these big power users such that we can shape the load and try to mitigate or use sort of big data in real time to speed up the reaction time that the grid needs to be able to support these huge energy demands instantaneously. But still, that means managing in a hierarchical way or control way of billions of potential sources or chargers and so on. And we don't even really do that well with the flow of data, which is relatively easy in comparison on the internet. And we've been trying to do that for decades. So I think there's some big challenges there, particularly at the local level in a grid. And the last but not least is the threat of cyber and physical attacks, some of which we've heard more about very recently. So these kind of attacks are both natural and man-made. Now, there have been hackers recently who've gotten into energy systems and exposed households to control blackouts and other industrial interferences and so on. And physical attacks, even people shooting up substations and other things, can really cause serious and difficult to repair damage. And then there's the long-term danger of things like electromagnetic pulse disruption from solar flares and other things, which some people are predicting to happen more frequently in the next decade or so. So these are major issues and can cause great devastation by putting the grid down for short or even in some cases long periods of time if the damage is pretty significant. There are technologies that are helping to control cyber attacks, if you will. Things, technology similar to blockchain or faster acting SCADA systems and so on. Which promise better protection on the cyber side. But physical infrastructure and power line vulnerability are not that easily or inexpensively protected. And for example, if you want to bury things underground or undersea, three-phase AC cabling is pretty expensive. And the fact that we have concentrated physical apparatus in substations and other routing hubs and such, power conversion equipment, transformers, and switching devices, they're all easy targets for causing debilitating damage if somebody really wants to try. So I talked about the challenge and I talked about some solutions, but there really is needed a better toolbox of solutions. And we really need to start by rethinking the grid sort of from the bottom up, because that's where the problem manifests itself, even though problems may be caused upstreams in many cases. So while we focus on trying to optimize the here and now in the existing grid and its technologies with practical set of economics, we need to also include thinking about provisioning for mutable openings to adaptation of the grid and adoption of new technologies, new business models, and new regulatory frameworks. And we have to, in that process, recognize the accelerating velocity of electronic and communication development. The two primary fuels of progressive change are really electricity and information. And one without the other is not going to make it for us. So human and financial resources need to be focused on changing grid infrastructure, if you will. Now, we can also change the way we operate the grid or operate a newly configured grid. We need to sort of change to a holonic operating model to make these kind of distributed investments economical. And that means that the grid needs to be not totally hierarchical controlled, but have its own resource of control embedded within it, particularly at the grid edge, where most of this action takes place and where a lot of the new energy production capability is coming from. So grid modernization needs to accommodate both these integrated, sometimes customer desired outcomes with the grid modernization of the existing grid. And last but not least, we really need to avoid just trying to build a new version of the old grid. Fundamentally, the grid was designed for largely to serve different loads and under different circumstances than those that the grid faces today. So grid architecture really needs to look at things differently and not just repeat the architecture that was built for needs years ago. So with that, let me start talking about where this all needs to go. If you were to say, what are some of the new attributes or key attributes of a sustainable grid solution or set of solutions, you'd have to say that, okay, when it comes to adding power, let's do it at the grid fringe. That's where it's used. That's where the power is used. And there's plenty of new technology and capability to do that. we need to share and reserve storage, but not necessarily centrally only, but at the grid edge as well. New generation storage and loads at the grid edge are natively direct current, so we need to recognize that. But that allows, if we use direct current, to move to a non-synchronous decoupled topologies, which are easier to manage and handle and configure in terms of making them self-healing and self-configuring in a sort of a mesh topology as opposed to a hub and spoke topology. And when it comes to control, if we use this kind of Hellenic, or each node in the grid is able to operate independently, but also in synchronous with the rest of the system, that the semi-autonomous distributed control is a part of that. But if we do all that and we put all this kind of effort in at the grid edge, we can start defining energy as a service, which gives grid operators and other business folks the ability to differentiate these grid services on the basis of capability. So again, that brings us to microgrids, and we think that microgrids are really the building blocks of this expanded, if you will, solution set. We really think that they're critical and important, but microgrids to some people are a little bit mysterious in the sense that some people think of microgrids as things that only utilities do with solar farms and fuel cells and things. Other people think of them as buildings or homes, but actually microgrids can come in all sizes, and therefore when you think about it, if you think about the analogy with the information system, you'd think of it as computers. We have computers as small as the ones that we put in our pocket, which is like a cell phone, to all the way up to supercomputers that are liquid cooled. They run so fast and hard at major research centers and insurance companies and such. So there's a whole spectrum of information system nodes, if you will. And I think that when we talk about microgrids in the power system, you need to have that same kind of thought process, that microgrids can be scaled at any size and applied in all these different applications, from as small as a room or an apartment or a floor of a building, all the way up to utility grids that house massive solar farms and storage capability. And there are many types of microgrids. There are microgrids that are kind of simple and only handle demand, or there are ones that are owned by corporations, or they're next to substations. There are DC microgrids, AC microgrids, hybrid microgrids. The kind of power that they supply can even differ. Can supply AC or DC power, or some intermediary form of power that needs to be converted somewhere along the way. Or you have hybrid topologies and how these microgrids get hooked together. So microgrids, the term microgrid is somewhat of a term similar to, say, computer or network, where unless you define it, it doesn't mean a lot to people. However, at the same time, microgrid has this really spectrum of capability and scalability. So that's a significant benefit in constructing systems with them. But the benefits of microgrids can solve some of the things, or service some of the ideas of that ideal list of things I talked about. They can add capacity and generate it at the fringe. They can provide storage, again, at the fringe or at the edge of the grid. They can incorporate all these new generation storage and loads using natively direct current in many cases. They can be non-synchronous and much easier to couple and route power within networks. They can be self-networking, where since you don't have to synchronize and such, you're really just looking at balancing power flow. They can be self-healing and self-configuring in many cases. And they can be operated with semi-autonomous distributed control, where essentially each the relationship between microgrids in the system are really managed at the point of interconnection and not from a hierarchical standpoint or a hierarchical control scheme. And last but not least, they do open up the floodgates to energy as a service as a differentiating and capability in the power system. Now, we at eMERGE see this kind of progression to a new format as something that's maybe not that easy to do when you first look at it. But if you decide that you're going to focus on this, what I would call a bottom-up architecture, it really makes the most sense. That's where the bottom tier, where all this new load is coming in, but also where a lot of the new sources are coming in, where these individual microgrids or nodes within the network would be responsible for their own optimization and their own reliability. But that also means that if they fail or they're interrupted, they don't bring down a whole system through a sort of a cascading linear progression of failures. So that means also that all these millions, maybe even billions of distributed energy resources and aggregators can be managed without the need for keeping track of them at high levels and concerning them. I don't know how you would do control a billion different sources and loads to shape and so on and so forth. It just it sounds impossible. So, but by breaking it down and having each node sort of self-manage, it makes the job a lot easier. And then the central command, if you want to call it that, is really relegated to those few points of connection back to the more traditional grid scheme. Now, there's a lot to figure out here with this new architecture. But eMERGE, and the association that I'm involved with, among others, is really helping to address the technical and needs in terms of standards and to try to coordinate a framework within which this can all take place. We particularly focus on a greater use of direct current technology in these microgrids, and which makes the sort of grid-to-grid interconnection or networking scheme much easier to do. We understand we're in these kind of turbulent times where some people would say the energy system is approaching chaos, whether it's from political, the likes, or technical problems, or all these issues that I just spoke of earlier. So utilities in particular and regulators alike are kind of nervous about what's ahead. And only really a bolder utility or two can maybe show the way. So what we really are looking for is that demonstration that could spark a wave of reform and new innovation in the grid. That reminds me that's why we invited today's guest, Rob Bennett. Now, Rob, if you could open your mic and just say hello, so we know you're there.
Good afternoon. Thanks, Brian.
Hey, Rob. Let me tell people for a second just a little bit about you, because I'm not sure that many people have met you, and we've had the great honor and privilege to do so. But Rob is currently the president and CEO of Emera Technologies, and Emera Technologies is a non-regulated subsidiary company of Emera Inc. And he is a former Emera utility company top executive. He started, back when the utility now known as Emera was just Nova Scotia Power, I think was the name of the company. Is that right, Rob?
That's correct.
And Emera has now grown into one of the leading energy servers with over 2.5 million customers in Canada, in the U.S. and the Caribbean. An interesting diversity, actually, even of service areas. And from what I've read, Rob, you guys have been focused on, delivering cleaner and more reliable and safe energy, while at the same time really trying to be a cost leader as well, or at least not break the bank, so to speak. Now you've been at this for quite a while. I remember you telling me a little bit about some of your experiences, even looking at high voltage DC and such for long haul transmission. But rather than trying to predict how you view this whole world, particularly of microgrids and how they might help in the future, I'm going to let you talk about that. But to do so, and I know, most speakers like yourselves, and by the way, folks, Rob is an excellent speaker if you haven't heard him on some of the other blogs and things that he's done. But most speakers lead off with some kind of funny story and a punchline to get everybody's attention, But I think Rob has a very serious story to tell us that all started to take place on September 27th, 2022. And many of you may know that date. And he'll maybe tell you some of the days after that day. And that might be of interest to this audience. So, Rob, can you tell us what actually was going on at that time?
Well, thank you for the very kind introduction, Brian. That's very kind of you. And good afternoon, everyone. Yes, last year, September 27th, anybody who's ever experienced a hurricane knows it's no joke. And certainly that's the case if you live here in Florida. And last year, Hurricane Ian impacted the west coast of the state with devastating results up and down the west coast, but primarily in the Fort Myers area where there was a tragic loss of life. And then all over the west coast, loss of property and of course, power outages, hundreds of thousands of people without power across the state. And that's not an unusual thing for Florida. Once a year, probably, you can expect to have a really major storm that's going to knock out hundreds of thousands of customers. And being a former utility executive and Emera executive with over 30 years experience putting power back on, I've certainly had many nights and weekends and holidays and every other day working to reinstore power. But in the case of Hurricane Ian here in Florida, we had a different tool at our disposal. The tool is, of course, as Brian was saying, a microgrid, which we had installed earlier in 2022. And even though thousands of people in the area and people even within the broader community that our microgrid is located in were without power for several days, the fact is that our microgrid design performed flawlessly, and the customers there maintained their power without a bump or a flicker of any kind. And in subsequent discussions have been absolutely delighted that they were able to be a part of a microgrid community and realize that type of reliability. And the local utility that installed our microgrid, Tampa Electric, again, is very impressed with the performance and very happy with what this new microgrid technology can do. Because in the state of Florida and in many states, reliability is a big issue that needs to be addressed. It is being addressed, but the utilities need new tools to do that. And we're in the business of inventing those tools and promoting what can be done with a completely fresh set of thoughts and ideas on how we deliver and manage power.
So, Rob, this is kind of reminds me of a movie that I just watched for the first time called Grid Down, Power Up. But you guys are the real deal. I mean, the experience that you gave to those customers is not a movie; it's real, and you literally kept the lights on. But
it's a very sorry, Brian. It's extremely real, and I wish that we had the clips from the interviews of some of the customers that have been done down there, because it's that's the thing that keeps me going every day, is to see the reaction, the positive influence that we're having and the ability to bring in the amount of renewable energy that we're bringing in that community as well.
Well, that grid pilot is, to me at least, is sort of the poster child now of this new thinking about grid architecture. But I do want to back up a little bit and go back maybe 3 years or so with your expert and technical and operational background in utilities. What problems were you trying to solve when you first came up with this idea for a microgrid platform like this BlockEnergy platform?
Well, starting at the very beginning, Brian, I started in the electric utility industry as an electrical engineer, as I guess makes complete sense. So my whole experience in the business, whether it was an operational engineering role or a managerial role, or ultimately as a CEO or executive role, those roles have always been strongly influenced by the fact that the job is really about delivering safe, cost-effective, reliable energy to customers because they need it. It's part of our modern society. And after 30 years of doing that, I had learned a lot, had a lot of different experiences, and I was invited by Emera to embrace a little bit of freedom in terms of thinking about how things could be different. It's a space, the creative thinking or transformational strategic stuff was always kind of my forte, so it fit perfect with what I wanted to do. And fortunately, I have supporters, investors who supported the idea of starting with a completely clean slate. How would you do it today? How would we make energy, distribute energy today using the very best technologies that are available to us today? And that freedom really is, or that liberating position to have makes all the difference, because it allows you to think about more distributed energy resources without the constraints of a modern interconnected power system. Not to say that the power system is not critical to our design or immensely important all over the world. It certainly is. But maybe what we're doing in new communities where at least half of the load growth in the southern United States is taking place in new residential communities. So how are we facing that increasing need for electricity using the most modern technologies that can just do it a better way? And that's what we've created, I believe, in our microgrid designs, and that's what we're promoting today as a small part of how we might change the industry.
So there are many challenges that I outlined in the beginning of this. Are you seeing it that way? Are these challenges real? And is the solution set that you've at least started to deploy going to make a difference?
It's absolutely real. You can feel it. It's not just it's not the utilities that are faced with this. It's a societal issue around clean energy, and that's why there's been such a positive and significant movement by the federal government, for example, with incentives to move companies toward innovating in the space and creating change. It's absolutely necessary, and the utilities are right in the middle of it, and in the middle of it with maybe some disadvantages in that the utilities really don't have a mechanism to drive innovation within the utility structure. So, and that's rate-regulated utilities in general. So it's very hard for them to finance new ideas. So the rest of the world needs to think hard and create things that utilities can use that can move us all forward. And that's what we've been doing for the last 3 years. And whether those problems with utilities are just the normal pressures of increasing costs or increasing costs while at the same time as trying to make cleaner energy, doing that at the same time that there's tremendous growth in demand from electric vehicles and other electrification, at the same time that the grid is old and the ability to maintain all of that infrastructure and keep the lights on, quite frankly, gets harder and harder every day. in a world where everybody deserves to have electricity for sure, and to have access to that electricity in a secure way that's at a reasonable cost. It's a really tough job. So we're trying to do our part to help. And everybody recognizes that some of these quotes you can see here. It's common knowledge. And unfortunately, a lot of work is being done. We're trying to do it with utilities as fast as we can. Our model is primarily focused on creating utility solutions, which are a bit different than a behind the meter solution for clean energy or battery storage or many of the other direct consumer focused solutions we see. We think the utilities play a critical role in enabling people to be more efficient, enabling better interconnectivity at the grid edge, enabling people to make more of their own energy. I think the utilities' role is to help with that in whatever way that they can, but they need new technologies to do it in a way that's safe and secure and efficient and effective for all of us.
Yeah, and I think that there's no secret that, you know, people have a kind of a negative or wrong impression of utilities. As you mentioned, some of the restrictions on utilities and the resistance to embrace the renewable energy sources particularly at the grid edge, is not because utility people are against climate change mitigation and clean air and so on and so forth. It's because the technology is difficult given the traditional way of doing things, and in this case, research and development like the kind that Emera Technologies is doing is so critical to moving forward. And it's interesting that Tampa Electric is one of the first utilities to embrace this approach, and not just like many utilities are trying to do their best in adding resources at the central or central places and so on, and beefing up their transmission capability. But this is a game changer for sure. So yeah, the example that you're setting is really the first that we can see the path forward, sort of the light at the end of the tunnel, pardon the pun. But
it's absolutely an innovative approach to the microgrid concept, and it's one that really works and works well. Also, we should celebrate that the utilities are reacting, whether it's in microgrid deployment or studying the impact of microgrids, or other things like virtual power plants or whatever else is happening out there. They're really reacting, I think, positively to try to find a solution to a very, very complex problem. And
yeah, we're seeing that here at eMERGE, as well as more and more utilities are getting involved in our work, which is really focused on grid edge solutions, whether they're behind the meter or in front of the meter, and utility operated. I think for anybody to believe that everybody is going to be willing to put in their own electrical system and manage and operate it on a daily basis it is about as foolhardy or mistaken as people who think that utilities don't care about their customers in the way that they do. So this is, again, like I say, this is really a game changer in changing the whole view of what can happen going forward, where there's real cooperation and collaborative work up and down the stakeholder tree. So tell us though more about the actual block energy solution. Now, as we understand it, it's a type of a DC network, or at least it's DC linked or connected. Why? DC to some people is a distant thought, unless they're talking about their stereo or their computer or something like that. They haven't really applied it to thinking about bulk power and large power use. So looking at your system, it is different and very different. And are utilities and other system operators going to be interested in this? And if so, why?
Yes, thank you. And oh, that's good. Thanks. The fact is that we're surrounded by DC direct current energy. We just don't realize it, but it's everywhere. It's a more natural form of electricity than alternating current is, for sure. And I think that you made a point earlier. You said the idea of trying to synchronize and control millions or potentially billions of individual devices seems almost insurmountable. And there's got to be huge value in breaking things down into some type of modular configuration that can kind of take care of itself. That'll do all the things that we want: demand side management, efficiency improvement, whatever it is, reliability, but take care of itself. And that's really what this design is all about. It's a grid interconnected microgrid, and I think they all should be. There are tremendous values that come from being interconnected with a grid of any kind, whether it's a communications network or a power network. This grid that we built immediately changes from AC to direct current, and we distribute energy around the community in the direct format. And the very practical reason that we do that is because most of the energy in the community is made from solar panels, which are inherently DC. It's that energy is either directly used in the house or it's stored in a battery, which is DC. And since all of these devices are direct current, it makes tremendous sense and is much more efficient and cost effective to manage the flows of that energy around the community, the optimization and such, in a direct current format. And in our current design, of course, because many of the things in your home are alternating current powered, only to subsequently then usually be converted back to DC, but that's a different story. Because you need AC power in your home, we have a whole home inverter that creates a perfect 240 volt split, 120 240 volt split supply to the home that has a perfect sine wave with very low harmonic distortion and absolute stability. So we kind of make exactly what you need right at your doorstep where you need it. The fact that we do it with DC has many other advantages, and a big one is not needing to control the frequency, which helps us maintain stability. We've invented ways to protect this system, electrical protection for the system, that are very, very effective. And ultimately, that means that the interface to the grid can be stable and dynamic without any interruptions, as many people call it, seamless connection, disconnection from the AC grid. So it's proving to be a very, very effective way to provide energy. And what I'm getting even more excited about these days is ultimately the fact that the loads in your home that are DC powered will ultimately be switched over to some form of DC supply. And the reason for that is just because of efficiency gains. The biggest one that we'll see in the not too distant future is your electric vehicle. It's going to be significantly more efficient to charge that car using a DC platform. And we're building a system that's ready to do that.
So you're kind of future ready right from the get-go here, which is one of the points that I was trying to make earlier, that when we think about grid solutions and going forward, we really need to think about the future new sources of power, new loads. You know, like the internet. Did anybody think that you'd be running your security system or starting your car from your cell phone, just a few years ago? So electricity in a certain way is the same way, because information and electricity are the two major components of progress. And so electricity is likely to be used in all these new applications. There's going to be new ways of harvesting the rich resource of electricity that already exists in the environment and, in various commodities like hydrogen and so on and so forth. So I think that's one of the other really important attributes of this approach, is that you're kind of future ready in both directions, both in terms of sources as well as load configurations. The other thing that I think somewhat unique, well, it is unique, is that each one of these nodes in what you're showing here, the 9-home block loop and so on, each one of them has enough intelligence to operate on its own, but also enough intelligence to provide the minimum amount of communications that's necessary to be a participant in the network as well. And that's what I like to call a halonic, in a halonic existence, meaning it can operate alone or in tandem with everybody else. And that microprocessor or whatever you're using to put in there, and I thought about it. I said, well, isn't that really expensive to do and so on? No, we would never be able to afford to have that kind of control in every home and all that. But then you think of it and you say, yeah, you can, because your cell phone is almost capable of doing nearly that, and maybe not quite that. But so that's another big novel piece in here, is that you're really putting distributed intelligence throughout the system right from the get-go. So
that's right. Thank you for pointing that out. It's a fully autonomous system, so it can operate completely independent of the grid. But importantly, all of the assets here are designed to be in front of the meter, and that means they're a utility asset. Customers don't pay for this system. The utility installs it on their behalf. And because it's a utility asset, that means that all of these controls and batteries and solar panels are actually shared and optimized as a community. And while that may seem a little complex to optimize about 200 homes in a typical block energy installation, the algorithms that we've developed to do it are very effective, and it happens seamlessly in the background. It's interesting to watch on an operational diagram, all of the flows of energy moving between fences.
I wanted to get to that because you gave me a slide here that was the original pilot, I guess, at the Kirtland Air Force Base in New Mexico, right? And so you put this together, installed it on the military base there, but in probably the more personnel side of the base, not the war making side, if you will. But be that as it may, how did you know when you put this thing together that it would work, and who tested it to make sure that it did work?
Well, this was our demo site, our very first installation with our conceptual design, and we had a lot of confidence that it would work. But of course, we had to build something somewhere and stress test it. And Kirtland Air Force Base in Albuquerque, New Mexico, was the perfect place. We supply some base housing on the base. We have our own solar on the base housing, but we also interconnect with a large solar installation that's owned by the Department of Energy, which is their national solar test facility. And we also connect to the lab facilities for Sandia National Labs, a lab called DETL, which is their Distributed Energy Technologies Lab. So this is a trifecta of the DOE solar, the Air Force Base, and the national lab. So together, working with Sandia, we're there every day, improving and testing the performance of every new piece of equipment that we develop. And it's proven to be a fantastic collaboration and a fantastic site for us to just make the system better and better. And this is the key. This is the technology as it is today, but it gets better every week. And the devices that it's made of will continue to go down in price and improve in performance. So as time goes on, there's no question in my mind that this will be a dominant format for energy provision, particularly in new communities, because the best place to make change is when you're building something new. Let's do it a different way.
Yeah. And this is an engineering, I'll call it a prototype or something, pilot, but it's still operating, isn't it? I mean, this is real.
Oh, yes. It operates, supplies power, it harvests solar, moves it back and forth between the labs and the various buildings there, including car charging and other things that happen. And it's been running very well since 2019. It's our very first design. So our designs have gotten better since then, and I'm extremely proud of it. It's a wonderful place to visit, and it's where we take people when they want to go see what we're doing with microgrids in our test operations.
So back to the development in Florida with Lennar Homes. Maybe most people would know Lennar is one of the premier home builders in the country. Tell us a little bit more about that development and how it came about.
Right. Well, this development is in Sun City Center, which is about halfway down the west coast of Florida. It's a beautiful, relatively new community developed by a company called Metro Development here in Florida. And these homes are all built by Lennar Homes. Fantastic people, fantastic partners to work with. And this has been up and running since earlier last year. This is the community that I spoke of that was uninterrupted during the hurricane. I think we have a flyover, don't we, Brian? Is there a?
Yes, we do. There, and hopefully that's activated. Let's see.
See if that'll work.
There it goes. There it goes.
Yeah, it was just finishing construction at this point. We've integrated the solar right into the roof design of the home, and that's the thing about being able to do things when they're new. So all of this solar is owned by the local utility. The whole system is owned by the local utility. The solar is installed on a membrane on the roof, and the roof system is built around the solar. That means that we can remove the solar if we want without touching the roof, or the homeowner can redo the roof without touching the solar. So these are all important considerations when you're building front of the meter type assets. But maybe we're a little froze up there, Brian, but people get the point. It's just another beautiful community in Florida, except this one has one of the most advanced direct current microgrid power systems in the world.
So there's some questions, and let's take a short break here and answer some questions about this. Some people are asking what specific DC equipment or technology is deployed at each home. And I think the answer, yeah, go ahead.
Yeah, well, I think the next picture on there is a picture of the block box. So this is a day and night picture of what the system looks like beside your home. Putting the lights on it, by the way, was my idea for all the people who like that it lights up at night. Or it might have been my colleague Gary Opedal's idea, but anyway, doesn't matter. It was a good idea.
Don't worry, I had the same lights on my Ford 150, my F-150. So,
yeah. So this box sits discreetly beside the home, and inside of that box is a converter system that connects the box to the direct current grid system, that wire system that runs around the community that, of course, is buried underground. That converter then connects to a battery, and that battery subsequently is connected to the solar that's on the roof of the home, and it's connected to a whole home inverter that creates that perfect AC supply that then goes through a normal utility meter and into the home. So, and of course, in that box as well are the controls that create all of the optimization and collaboration with every other box in the neighborhood. So each of these boxes, you might describe it as having its own little personality. It knows what its home needs in terms of energy supply typically, and what the behaviors are. It has information or gets information daily on what the solar irradiance will be. It knows, of course, what its battery level is, and it communicates in a very innovative way with the rest of the boxes in the neighborhood to decide who's going to do what and how they're going to make the best use of all of the energy that can come off the roofs of all those homes in the community.
And another question came in about voltages. I assume that the voltage is very similar to what you would transport in an AC voltage, only it's DC. So wiring probably is similar, no? And it must be underground from what we see here.
Right, it's much lower voltage. Typically, the utility would distribute energy around a community like this using probably a 12 kV AC buried cable, crosslink polyethylene cable. We do it at 750 volts, so a much lower voltage. And the reason that we can do that is because moving energy around in about a square mile area is just more efficient using direct current. We all know that the direct current is 20-25% more effective in terms of use of copper, because of the way the system operates, we can use very low voltage systems.
Right. So most people have this kind of misnomer that when you use DC, you need bigger wires, but actually the opposite is true for an equivalent voltage. Is that pretty much the case?
It is. I wish I could show you the size of wire that actually runs to this block box that supplies the whole home, but it's very small, surprisingly small.
Well, we may say that for another one of these webinars. So stay tuned, Rob. We may call on you again.
Yeah.
But also, people are asking, how is this? You mentioned it's connected to the grid. Okay, so you have a DC kind of looks like a 2-tier. I saw a little community tier in there with some supplemental storage and power. But when you get to the grid, that's an AC grid. So what do you do there?
So at the interface to the grid, we have an inverter, of course, to invert back to AC or to accept energy from the grid if that's the way the system is set up to operate. There's a backup, usually gas-fired reciprocating engine at that point, which is the ultimate in system reliability, because when things like hurricanes happen, if they happen for a whole week, it's probably going to be cloudy. So while we can make some solar, it may not be enough to power the whole community. So there's supplemental generation at that point. And controls, of course, and a battery. That is kind of an interface, smoothing battery, extra storage for the whole system. What's important about the interface to the grid is, aside from being a single point of control for the utility operator, so all of these homes, the utility operator can burrow down through his control screen and see what's going on at every house inside of every box. But for the most part, they just need to know what's happening at that node on their feeder. And they have full control over energy import, energy export, VAR control, all of the things that are very handy, in fact, critical today for the distribution grid operator to have control over. And just in terms of the utility interface, Brian, the primary interface advantage for the utility is that they set this up. They have complete access and can manipulate the control system in here any way that they want to. And in this particular case, the utility sets it up so that this community is never connected to the grid during the daily peaks in both winter and summer, which happen at different times. So in the summertime, it's an evening peak in this part of Florida, and in the wintertime, it's a morning peak. So each day, the control system sets itself up so that it ensures it's not drawing energy from the system during those peak periods.
Right. So again, the interface with the utility is interactive in the sense that it's a bidirectional. And in essence, I suppose that the 37 home network that you have can also provide some supplemental service to the grid when necessary. Frequency support or other things that, after the power's been inverted. Somebody asked whether the voltage in the home is 750 volts. And I think you explained, no, that's the DC link voltage, but the actual voltage in the home, in this case, at least, is the 12240 AC, which is achieved as a pure sine wave AC, which I'd like to point out to people who are not familiar with it, is probably the best AC you'll ever get, because it's not corrupted by anything that might be problematic on the normal utility lines and so on. So how about the one last question, and this gets a little bit away from the technical side, but more to the financial side or what have you, are the homeowners in this neighborhood now paying a premium because they they have this backup. I mean, after all, it had to be tough for their neighbors to look over and see this neighborhood fully lit while they were trying to boil water and do whatever they need to do when the power's off.
Well, people in this neighborhood are very proud of these boxes. I can tell you, they think these are wonderful, and many of them, I'm sure, were happy to entertain their neighbors and friends from the community who didn't have power, and they were able to help out, which is great. But no, they don't pay any premium. The key to this whole design is that the electric utilities, when they're planning and connecting new communities, they have choices to make about the power supply to that community. And if they can avoid the cost of building new generation plants, building new transmission lines, building new distribution lines, and instead implement technologies like microgrids at the grid edge that are equally cost effective, in fact, better in terms of cost profile than doing it the old fashioned way, then that's good for all customers on the network. That helps everybody. And therefore, these customers pay the exact same price as any other customer on the grid. Yet they get the solar and they get an extraordinarily beneficial reliability result, which everybody loves.
So each of these homes, just to repeat now, each of these homes is an independent microgrid in a sense. So one home, if all the other homes somehow got damaged or whatever, and there was one home that didn't get damaged, it would still operate with its lights on, et cetera, right? And let's take the case where, say, a few of the homes do get damaged. Do the other homes, are they affected, or is it kind of, the network kind of route around the problem and all the other homes are still good to go?
No, the network is to a large degree self-healing. And one of the great advantages of having these independent nanogrids, as we call them, is that maintenance on the system can be done so much more easily. We can de-energize the whole components of the system to replace things or test things without affecting a customer at all. So I believe it will prove to be a much lower long-term cost of operation than the traditional way of supplying power.
Okay. Sorry, Robert, we're kind of running low on time, so I just want to sneak in a few more slides for those people who can stay with us for a few minutes here. You sent me a slide on Fairmont Heights. Now, Fairmont Heights, as I understand it, is an affordable housing project that is going to go up probably sometime this year. And so this works regardless of the type of housing, right? Or
the business model works no matter what. Low-income installations need power. They have rooftops. They need to be connected to the grid. Microgrids are a great way to do it. It's completely equitable, and I think very future focused. So this one's happening with the utility Pepco in Maryland, and it's under construction right now, actually.
And other people ask, you mentioned natural gas as a sort of a backup at the community level. Does hydrogen eventually have a play here as well?
The great thing about our DC technology is you can connect whatever kind of generation energy source you want. As you know, Brian, well, better than many, that the flexibility of the conversion technology for DC just means that when we're not managing, trying to synchronize and manage frequency, and we have extraordinarily broad bandwidth of voltage that we can accommodate, then interfacing to other devices like fuel cells or reciprocating hydrogen generators or more solar at a community level or electric vehicles, whatever, it all works.
Well, there's a bunch of other questions that have come in, but I'm afraid that we're going to have to answer those by email. So all of you who did submit a question that wasn't answered by Rob here live, we'll try to answer those and send you an email on the answer. But we're just summarizing the project results here. As I mentioned, the recent movie Grid Down, Power Up. This is the real story. This is the real deal. I like to think of this story as the little grid that could. Right now, 37 homes, but it could have been 3,700 homes or 3,700,000 homes. I mean, the proof really was in the pudding when Hurricane Ian hit, and things kept chugging here. Also, thank you for sharing with us the lessons that you learned and applied to the design and implementation of this type of architecture. I suspect that you're happy with the results in terms of resiliency and the deployment of renewables within the system without the fear of destabilization of the traditional grid. And really, this whole approach makes microgrids at this level, at the grid edge, really relevant. So thank you, Rob, for all of that and your explanations today. I know you have a quote here that said microgrids are the best strategy for energy assurance. And I guess you really just put the punctuation mark on it by describing what the Block Energy platform has done. And I would imagine you probably won't be the only company to go down this path of distributed energy and network microgrids, but certainly leading the way, particularly with your operating company background and your association with Emera Inc., has got to give some people pause to really think more and hard about how we don't just build more of the old stuff and really move to a new paradigm here. So again, thank you. Thank you for answering all those questions. I want to remind our viewers and listeners that our next webinar is on February 14th. The picture there is actually wrong. That still says utility scale, but we're going to be talking about remote and remote access to electricity that are off grid, essentially. That doesn't necessarily mean single entities off grid, in the backwoods, but particularly for things like cell towers and communities that don't have access to a grid. Probably not too many places like that in the U.S., but there are places like that for sure around the world, and we'll be talking about those as well. And if you're not already or haven't considered membership in eMERGE, we invite you to do so. We are developing Vanguard standards that embrace some of the things that Rob talked about and that others are implementing in this real challenge for energy for the future. We also work to really catalyze market development. Webinars like this and our participation in trade shows is helping us do that. And we provide education for the industry and for even down to consumers from time to time. So if you're not a member yet, you might want to consider it. It's a great organization, and you can contact Brenda Lovell, who is our Director of Membership Relations. And that kind of concludes today's webinar. Again, thank you, Rob. A phenomenal presentation and discussion. Congrats to you and your team. Really well done. I mean, game-changing, well done, if you will. And we'll see you all in Boston. So thank you, everybody, for staying tuned and letting us go over a few minutes here. Thanks.
Thanks, Brian. Keep doing what you're doing. Thank you.
Thanks, Rob. Good be. Thanks.